Thanks for introducing me. I'm one of the two weird people of this conference that are working with looking up instead of looking down. We're from the atmosphere, so I'll be talking about parameterization of internal gravity waves, not eddies in general, but specifically internal gravity waves and in an atmospheric context. And there's we do that in quite a special way, and I'll explain you how exactly. But to get you into the mood for the atmosphere, I have a picture of what clouds. All right. So I would like you to look at this region here over central Greece. There's a mountain range here, which is called the Pindos mountain range. And in this image, this is from Easter 2019. There was a wind blowing from the southwest over the mountain range, generating so-called V waves or orographic gravity waves. And you can see these phase lines in the clouds. And if you go forward by 3 hours, you can see the phase lines are exactly stationary, which is one of the major properties of orographic waves. And so I can swap a little back and forth between different shots from the satellites, and you can see those phase lines are exactly stationary. So these are the internal gravity waves. We know they do make a difference. They are quite important in the atmosphere. And these have a wavelength of around 6 kilometers at 15 kilometers, and a typical resolution of a high resolution weather forecast model is around 6 kilometers. So those would not be properly resolved. All right, so we're parameterizing internal gravity waves with ray tracing techniques, and we've already heard some, just that this is a tiny bit more complicated, and you'll see. All right. I'll jump into this very, very complicated slide, but I'll walk you through it one by one. The first thing is we work with the non-dimensional compressible Euler equations. So these are compressible. There is effects that you will not see in the ocean. And we build on these equations that I don't show, we build a multi-scale theory where the Rossby number is a small parameter. And then we decompose the flow into 3 parts. First is a reference atmosphere, as shown in blue. Then there's a mean flow expansion, as shown in red. And then there is a superimposing wave expansion, as shown in black. And the sums over the betas that you see here, these are basically that we have many waves. One thing I have to add, though, is that albeit this is strictly speaking nonlinear waves, we do explicitly neglect wave-wave interactions. We've worked on this in the past, but this is off the scope for this work. And then, of course, we have the full field, which is the reference part, the mean flow part, and the superimposing waves. And from these phase exponentials, we know that the extrinsic frequency is just the temporal derivative of the phase, and the wave numbers are just the spatial gradients of the phase. And then we get the following results. I like to call these the Brotherton-Gramshaw modulation equations, usually just called the modulation equations. And you have the following ones, which are very, very important. The first thing is the dispersion relation. I like to highlight one thing in the dispersion relation, which is the Doppler term is very important in the atmosphere because our mean flows are not just a couple of centimeters a second, but they are up to, in the jets, up to 100 meters a second. So these are really, really big terms. Modulation is very, very big deal. Actually, probably more important than wave-wave interactions. Then we have the Coulomb equations, which describe the evolution of the wave numbers along the characteristic of the wave propagation. The polarization relations I don't show because they're too long. And then one thing I want to highlight in particular is that we use a wave action conservation, but not in a classical way, but in a 6-dimensional phase space way. So suppose you can expand your classical wave action into a function of wave number and position in time. And then the waves actually evolve through this 6-dimensional space, and instead of building practically a Lagrangian theory in K-space and only evolving in physical space. The reason why we do this is because this allows us to avoid caustics in ray tracing problems. One thing I'd like to particularly highlight is that in that case, the phase space volume is always conserved. That is the position gradient of group velocity plus the phase-space gradient of the change of wave numbers along the trajectories is always 0, which allows us to rewrite equation 6, which is the wave action conservation, into from this flux form into an advection form. What is more, we of course, when we want to simulate the Earth, which is a ball, right? We can't use Cartesian coordinates as we've done here. We actually want to use Voelker coordinates. So I just put down what this means. We have not a change in position in x, y, and z, but in latitude and longitude, latitude, and radius. And then we have the wave numbers along the constant latitude, constant longitude, and constant radius. And then there's one thing to consider, and these are the terms in red. There's, because of the coordinate transform, there's so-called metric terms, which ensure that the waves propagate into the right direction. And as before, we have the wave conservation, the wave action conservation here. It's written in the advection form, which then tells us up to some dissipation. I'm going to specify later. The phase-space wave action density is actually conserved. All right. Now, in these equations, we have a modulation by the mean flow. These are the black terms here. These are the mean flow gradients, which modulate the waves, as we've seen, for instance, in Peter's talk earlier. But these waves are non-linearly interacting with the mean flow, so they're also generating a mean flow, and that's in the following description. First thing is, we do not make the assumption that our mean flow is geostrophic, purely horizontal, and hydrostatic, because that's the leading order solution when we have small Rossby numbers. However, in that approximation, there is no entropy flux convergence, and there's no elastic term. By the way, the elastic term emerges from the compressibility of the system. As Junhong Wei has shown, using all three terms leads to a way better agreement than just the typical pseudo momentum flux convergence that you may find in many parameterizations. All right, now we have all the tools. We know how the waves evolve. We have the Conley equations. We have a phase space, wave action density. We know how the waves are modulated by the mean flow, and we know how the waves modulate the mean flow. Now let's go and put this into a Lagrangian discretization. It works as follows. I have a schematic here on how we do this. Now this is just in 2 instead of 6 dimensions. Turned out 6 dimensions are hard to draw in 2D. So we have on the y-axis the vertical, and on the x-axis the vertical wave number. And now we want to span the space by our small rays or our ray volumes. So we have a carrier ray, these are the dots in the middle, and we construct a little volume around this. And this little volume evolves with the properties of the carrier ray, but can also compress and stretch in this 2D field. So they can, actually that's due to the numerics, they can actually glide apart a little, or they can overlap. However, the whole area is always conserved. So in theory, the red box around my initial box should always be, the area should be conserved. And then we maybe integrate some delta t, and the area of the individual ray volumes will be conserved, but it's not going to be exactly the same as the area of the red box, which might be deforming anyways. Then there's 2 things we need to consider when we want to have our waves interact with the mean flow. One thing is we need the mean flow properties at the position of the Lagrangian position of the rays, which is we basically just to do linearly interpolation from the grid to the ray position. That's the simple part. The more difficult part is we want to know what the waves do to the mean flow. And in that case, say we want to know what the acceleration of the mean flow at our Zn is, but we have a lot of ray volumes in this here 2D space. Then first of all, what we have to do is we integrate an M. That's part of the construction of the phase-space wave action density, but also we average in Z for a region around this Zn that we want to know it. And that comes with some damping, but that's part of the numerical errors that are small. All right, so to show you what this looks like, usually I have a video here. I'll just show a couple a couple of frames. What you see on the right side is one column in the model, and this is from the columnar version of what we do. You see the blue dots, these are our little rays. The red line is the pseudo-momentum flux. Its vertical gradient is going to accelerate a horizontal mean flow. And you see there's a launch level down here, and the maximum wave drag, you're going to see that later, at around 100 kilometers. Now, if we progress in time, those little ray volumes, they propagate up. Some of them might actually be reflected, so the vertical wave number changes to negative, from negative to positive values, so those will be traveling down instead of up. And then we see once the rays propagate to large heights, here and 120 kilometers, then we have a stronger pseudo momentum flux, U prime W prime, because of the inelastic amplification. Does everyone know what inelastic amplification means? Who doesn't? All right, okay. If, say, energy is conserved, wave energy plus wave-induced mean flow energy, the sum of this is conserved. Now, if we travel upward in the atmosphere, the density goes down exponentially. But if energy is conserved, which is rho times u square, then the amplitude needs to go up. And that effect is called inelastic amplification. In other words, gravity waves, when they're very, very small perturbation in the troposphere, they propagate to the stratosphere or the mesosphere further up, they become really big. So they have winds associated, which are tens of meters per second. So they're really strong. Which is also why we need this, right? We need them high up because they're going to break there, they're going to deposit energy, and they're going to change the mean flow. So this is what this is about. But we don't only parameterize in the vertical, we also parameterize propagation in the horizontal. And this is a little view, very similar to the cloud picture. You see central V's on the bottom. And the triangular cells of the Icon model that we work with. And this little hatched box is our ray volume now. And it may propagate from one cell to another, indicated by the arrow. And its source cell would be the white triangle as shown on the graph. And it might be traveling to the maybe dark shaded gray area. And in order to efficiently parallelize this, and this is very important with in an MPI style parallelization, we need some kind of handover procedure. And so there's a procedure where each cell, like here, the dark gray cell, is searching all the neighboring cells for ray volumes that might have traveled into the cell. And in that way, we can have a cell-based ray handling. And so we can parallelize the integration of the ray volumes in blocks, in MPI blocks, as commonly done. All right, two more technical notes. One thing is, wave breaking is parameterized with a Linson type wave saturation scheme. That is, as soon as the wave amplitude hits the threshold for static instability, the energy is dissipated. And the second part is our background wave sources that we inject the energy with. Besides the convective waves, which are also included, there's a physical form. I'm not going to go into this, but the background wave sources are in all directions alike. So we launch rays in all directions locally in each cell and leave the filtering of these waves with critical layers to the flow. All right. Last technical note, we implement this into the upper atmosphere icon. That is the icon model with the upper atmosphere extension. And that has an icosahedral non-hydrostatic setup with triangular cells as shown in the sketch. Now, our resolution is R2B4. That means around 160 kilometers resolution. That's coarse on purpose. We have 120 vertical layers, and our model top is around 150 kilometers. And we parameterize the non-orographic wave track while we do not touch the orographic waves, which are the ones that I showed in the cloud structure in the beginning. And we consider convective sources, background sources, and we calculate composites for 8 years for June and December with initial conditions from IFS. All right, let's get into some results. First of all, the one thing everyone always looks at is the zonal mean, zonal wind. You can see 3 panels here. The left panel is for the 1D implementation of the ray tracing parameterization. The center panel is for the 3D implementation of the gravity wave parameterization. The right side is the climatology to compare to. And we can see two things. One is in both parameterizations, there's a problem on the summer hemisphere. This is in June, so the northern hemisphere is the summer hemisphere. This is actually unrelated to the gravity wave parameterization. We can tune as much as we want. This bias is not going to go away. But there's one bias here for the 3D parameterization. Now this is run with exactly the same settings as the 1D, but we can see that the jet, which should be leaning towards the equator, is leaning poleward, and we've done some tuning, and the the runs for this should actually be done by now, maybe tomorrow. There's a similar picture for the southern hemispheric summer, and we see actually the 3D propagation can even mend some biases that we have there. All right, but the message here is the parameterization does a job in the sense that there is a comparable mean flow. So that the zonal mean, zonal wind would be very, very different if we switch off the gravity wave parameterization in total. Now let's look at the horizontal momentum flux distributions, and that's particularly interesting because we don't get that or it's very hard to analyze this from high resolution models. What you can see here is the top panel for the 1D version, the bottom panel for the 3D version. And there's a couple of differences I'd like to highlight. The first thing is, if we look into the tropics where there's no background sources, but only convectively launched gravity waves, then we can see that in the 3D version, this is more spread out, which is what you'd expect, because if there is convection only in a specific cell in the tropics at a specific time, this is the only cell there's gravity waves when there's no horizontal propagation. So in the tropics, the gravity wave response will be somewhat smeared out, whereas if we compare the extratropics, in the 1D version, because there's a constant background source, this is a lot more uniform than in the 3D version, and that's also because of the refraction patterns. So if gravity waves can refract around the jet and into the jets, they're going to lead to very different horizontal distributions, and that's kind of the take-home message here. Then another thing that atmospheric people always look at is intermittency. What you can see on the bottom is pretty much what you could see here, just that this is a snapshot, and this is an average over 8 years. On the left side, it's the 1D version. On the right side is the 3D version. They look fairly similar. However, if we look at the statistics of this, say we average around a band from 50 to 65 degrees south, and we look at how does the probability of the occurrence of momentum fluxes change. And if we look at the background waves only, we see we separate those. We see the top 3 panels. The left part is convective gravity waves, the center part is the background gravity waves, and the right is the combined. Now for the convective gravity waves, there's an intermittency also in a columnar approach, because there's an intermittency in when convection occurs. Now if we look at the background sources, you see 3 lines. The blue line is a steady state parameterization, which is usually used these days. So state of the art is steady state, not transient. Then there's no variability for background waves at all, which is clear because there's a constant source, so this doesn't vary. But we got a variability which is very close to, or way better, way closer to observations when we introduce transients. So in other words, if we look at a specific height, the amount of wave drag inserted at this specific height is going to change depending on whether our waves are assumed to propagate immediately from the bottom to this height, or if they can have a group velocity which is sometimes slower, sometimes faster, and they can propagate in 1D or 3D. So depending on where the waves are and when they are, there's a different statistics of the waves, which is important for some phenomena. Now this shows even more when we look at the Gini coefficients, which are statistical measure for this. I'm not going to go too much into detail, but this is just to show you that the statistics of gravity waves significantly change when we allow for only columnar propagation of gravity waves, or we allow for a three-dimensional propagation of gravity waves. There's a paper in preparation by Georg in this, and these figures are his quotes. One more thing we can do with this, because we have a three-dimensional pictures and we got a three-dimensional resolution of the gravity waves, is we can look at the wave action equation. Now, this is the wave action equation similar to what we had before, just integrated in the wave number space and averaged in time. So I have these three terms. One is the change of wave action over time, and if I average over time long enough, this is not going to matter. Then there's a horizontal propagation term, there's a vertical propagation term, and a dissipation term. So let's look into these.
Sorry, it's maybe 1-2 minutes left.
All right, great. I'm almost done. We can see in the one-dimensional version, the vertical propagation or vertical flux of wave action balances the dissipation. This is the classical picture, something we know. But if we go to the 3D version, we see that refraction changes the picture significantly. As our waves can be refracted out of the jets or into the jets. We see convergence zones like around the southern polar jet, and these three balance and they have the same magnitude. That means horizontal propagation cannot be neglected as it usually is. Finally, a very good example for this is the southern polar jet. So this is the jet around the South Pole for the 1D run on the left side and the three-dimensional run on the right side. And the color shading is the meridional momentum flux. So that's in north-south direction. And if one would have a horizontal flux, which is however they don't propagate, in the 1D version, this is actually really random. And also the jet shown in the contour lines is very cyclic around the South Pole. However, what actually really happens, and that's very close to observations, is that, first of all, the southern pole, the winter jet, is somewhat shifted from the South Pole. That's why this looks like an open donut. And also we see that south of the jet, there's a northward propagation into the jet, and north of the jet, we have a southward propagation into the jet. So because of the jet and wave numbers being retrograde, there's a refraction of waves into a jet, and that's something that is observed typically, but usually not resolved by the models. All right, in summary, MS-GWaM is a Lagrangian ray tracing scheme for internal gravity waves. It allows for three-dimensional transient propagation, which is important as we have seen, and parameterizes non-orthographic gravity waves in the upper atmosphere ICAN in a highly parallelized and efficient way. And the results show that we get a reasonable agreement in the zonal mean fields. We have physical intermittency, we have physical refraction behavior, and we can show how important the three-dimensional transience is. And finally, that's maybe the most important take-home message, is that it's a powerful tool to investigate the global three-dimensional gravity wave behavior. Thanks.